I'm happy to introduce Thomas Lesgourgues, who's a postdoc here, who works on extremal and probabilistic combinatorics and graph decompositions, and completed his PhD in Ramsey theory at the University of New South Wales in Australia, and has a master's in discrete mathematics from 2019, and another master's in statistics and economics from 2009. And if you notice the big gap, he was actually a financial consultant for those 10 years. And warms my heart to see us scoop someone from finance into discrete mathematics rather than the reverse. So happy to have you. Please take it away.
Thank you, Sam. And thank you all for coming. I was not expecting that many people on the first week of winter. So that's a nice surprise. So today I'm going to talk about the topic in Ramsey theory. So not really what I'm doing now with Luc, but a topic we started working on while I was in Sydney with some of my co-authors. So it's a joint work with Simona Boyadjiska, which is she's a postdoc now. She moved to Budapest with the Rennie Institute. Shagnik Das, he's a professor in Taiwan. He moved recently. And Kalina Petrova, she's a postdoc in Vienna. So before we start, I'm going to be talking about graphs today. So there's just two things you might want to know about graphs. And that's it, which is graph or point of object with vertices and edges. And there's only two graphs you need to care for today, which is the complete graph, a graph on t vertices and all edges possible. So we denote by kt. And what we call the complete bipartite graph, kst, where you have two blobs of vertices, s here, t here, all the edges in between, and nothing in the blobs. So these two notations, kt and kst, the only one you need to care about. So before I dive into the topic, I wanted to make sure that you have at least that notion. And as I said, I want to talk about a topic in Ramsey theory called Odd-Ramsey numbers. And before I dive into there, I just want to give you a bit of background, because otherwise, if I just give you a definition of some Ramsey numbers, some weird stuff, you're going to say, why do we care? Because it's a bit weird, like often what we do in combinatorics. It seems weird without backup. So the history of that problem is fairly recent. So it started like 15 years ago in one of Tim Gower's weblog. He has an amazing weblog where he talks sometimes about a specific topic. And he was discussing a notion in what's called in Ramsey theory, you don't need to know that, the Alès-Jewett theorem. It's a very powerful theorem. There are still some open version, like open density version for that theorem. And they were discussing in the comment between himself, his past PhD students, and Gil Kalai. And the reason I'm mentioning that, it's the first time someone talked about something. You don't need to read that. But Gil was the first one to mention something called a graph code. So what is a graph code? I'm going to give you the definition. I'm going to go straight into like an example, I think. A graph code, as it's been defined by Noga Alon, like maybe some years ago now, it's a very simple object in some sense. Let's say that you have a collection of graphs, H, big H. So in my example, big H is going to be just a family of all possible triangles. So here I'm just drawing the triangle. You might have some isolated vertices. But H is my family of all triangles I can have in form of graph. And I say that if I have another collection of graphs on n vertices, F, I'm saying that it is an H code if whenever you take like two of them, so you look at the pairwise, what we call symmetric difference. So you kind of look at, you kind of sum the two of them modulo 2. So you look at, do we have an edge in here and not in here, or the opposite? So you look at the symmetric difference between any two elements, and you don't want the symmetric difference to be in H. So for instance, that family here, if you look at any two of them, you take the symmetric difference, it's never a triangle. While this one, it's not an H code, because what's the example? You look at that one plus that one, it gets something that is isomorphic to a triangle. So it's a bit not standard if you've never seen it, but there's a reason why we look at these quite often now. So that's what we call, that's not an H code, and that's an H code. And why do we call these graph codes?
Can I ask a question?
Yeah.
Sorry. So just, I think think you said this, but it's a triangle plus isolated vertex.
Yeah, you might have something, because otherwise, yeah. Usually, there's some small caveat, like you want H to be a family that is closed under isomorphism. So if you have one graph, you've got all the isomorphic graph to that one, for instance, and so forth. But yeah, you could have isolated vertices. You must have isolated vertices. Yeah. And why do we talk about graph code? There is an equivalence. When you think about graphs, quite often we do something is we assimilate a graph with its edge set. So we just think about the edges in a graph. And you can always like give an ordering on the set of all possible edges of a graph from 1 to n choose 2. So if you have a graph of n vertices, the total number of edges is n choose 2. And you just put a 1 if there is an edge, 0 if there is no edge. So you can assimilate a graph G, which kind of a binary strings of length n choose 2. So there is an equivalence problem. And now, what's an edge code? It's a family of graphs here, but you can see that as maybe a code word if you've been doing coding theory. It's a code word over the finite field of 2 elements, such that if you have any 2 of them, then the symmetric difference, or the sum modulo 2, is not in H. And now, if I decide that H, my family initially, what I was in the triangle, for instance, if I decide that in H, I've got all the graph with at most D edges, it means that in my H code, no 2 graphs sum to something with weight more than D. Okay? So it's, you retrieve in that case the concept of minimum distance of linear code. So that's a wide generalization of binary linear code, except now you care about the structures of the thing you want to avoid. So that's why Gil Kalai initially talked about graph codes, and it's a very, very active area of research. So that definition here from Noga is quite recent. A few years ago, he made an article called Graph Codes. It's when you're the first one, you can do that. And it's a very active research, but it's not exactly what I'm going to talk about today, just still the background. And because quite often, in this type of question, the same way when you do coding theory, you want to know how big can my code be. Okay? I've got a family, F, which is an H code. That it has many graphs, and I want to see how big can it be. That's a standard question. What's the maximum density of the maximum size of an H code? And what Noga did in his article, is he gave a general way to compute that values, at least to give a lower bound. So
When you say fixed states, do you mean fixed family or fixed single?
That's so. In that example, it's a fixed one. So for a triangle, but you could do the same for a fixed family. Quite often, yeah, something I should have mentioned. In here, I use curly H for a family when there is just one graph. For instance, when it was all possible triangles, we said just H, like a normal H. It's just a shortcut, just easier to think about. But yeah. And what Noga managed to find, he gave a wonderful proof that minimum density, the maximum density of an H code, is at least polynomial in that parameter here. And that parameter here is what we're going to talk about today is what's known as the Odd-Ramsey number of H. Okay. So that just to give you the background, and I will tell you after that what is the Odd-Ramsey of H. So the Odd-Ramsey number, and I will keep that definition up there quite a lot, and I'm going to give you some example after that. So don't worry, it's always a bit weird. Ramsey numbers, it takes a while to understand the mechanism sometimes. But the Odd-Ramsey number, if I give you either a graph H or a family H, is the smallest number of colors possible, such that you can color the complete graph Kn. So remember the graph Kn and vertices, all edges possible. You can color the edges of the complete graph Kn such that every copy of every H in that family contains a color that appears only an odd number of times. So what we call odd color class. So I'm going to give you an example just to be sure that you understand the concept. The proof that this number gives you a lower bound, it's a beautiful proof once again. I wanted to talk about that, but no, it's just too long for today. So just go and read the article if you have time. It's fairly short, and it's really well written. But the main point for us today is going to be that parameters, Odd-Ramsey numbers. So just to give you an example, to be sure that we all understand, because that's the main point of the talk, here I have what I claim to be a 5 coloring, so a coloring with 5 colors of the edge of K5, such that every copy of C4, which is cycles of length 4, contains the odd color class. So what it means, if you look at that coloring, and in here, you look at all possible C4. So that's one example. I've got a cycle of length 4, and it contains one odd color class, because, for instance, the blue appears once. So 1 is odd, it's 1. You look at another cycle, you got the green one, etc. And you look at all possible cycles, you're going to have at least one color that appears an odd number of times. So it's not easy. We call that Odd-Ramsey number because if you replace the condition that every copy has an odd color class by saying that every copy contains at least 2 colors, you get back kind of the inverse Ramsey number. The inverse Ramsey number is saying that you want a coloring such that every copy is either is or isn't monochromatic. So if you replace that condition by contains at least 2 colors, you get back the Ramsey number. So that's what we call odd Ramsey numbers. So it's a fairly new parameters. We're not the first one to think about the other one, but it's quite fun to play with. It seems easy sometimes and just impossible other times. So what do we know about that number? I'm going to just spit out some trivial fact, again, just to be familiar with the domain. If I give you any family of graph H, I'm claiming that the Odd-Ramsey number of that family is at most quadratic in n. Why? Because the number of edges in Kn is quadratic. So if I give you a complete graph here on n vertices, you use one color different for every edge, then clearly any graph you take, I don't care what H is, but any graph would contain at least one edge, and that edge is going to be unique in that colors. One is odd, you're good. So we know that the Odd-Ramsey number, or at most, quadratic. We know that if I give you just one graph here, contains an odd number of edges. So you want to say that you want a coloring such that every copy of that graph H has an odd color class. Well, just color everything with the same color. It's monochromatic, but H itself has an odd number of edges. So yeah, so clearly it has an odd color class. So that's kind of trivial case where we don't care usually. That's why quite often in that presentation, I will be talking only about graph with an even number of edges. And finally, that's mostly only if you do a bit of Ramsey or combinatorics. Otherwise, you don't have to think about that one. We have an easy upper bound, which is given by something called the generalized Ramsey number. So Luc and Michel have some articles in there. There's many good people working. It's mostly like you replace that condition by saying that every copy contains Q colors. So Ramsey number is saying that every copy contains 2 colors. Generalized Ramsey number is saying every copy contains Q colors, and we say odd. And it's just now a pigeonhole principle to say that if you have at least the number of colors to be at least half the number of edges, then you have one color appear only once. So that gives you a trivial upper bound. But that's mostly just if you are interested in the topic. Otherwise, I would say that the main fact that you should remember is that odd number of edges, it's 1. And that should mean that at least you understand what we're looking at. Okay. So that is the parameter of interest. And if I give you just a tiny bit of history, so again, it's been mostly introduced by Noga alone. And what he did, I think it was 2 to 3 years ago, when he introduced the parameters, he started looking at some easy case maybe, and he solved the value of that parameter when H is a star, so one vertex with all possible, all edges around them on 2K vertices, even matching, which are just like isolated edges, and a family of all complete graph, or all clicks K. And he solved, asymptotically at least, the value of the Odd-Ramsey number for these parameters. And after him, there's been quite a lot of study to trying to solve what's happening for the Odd-Ramsey number for clicks. So again, you try to color the complete graph such that every copy of a given click, like K4 for instance, or K5, contains one odd colors. And the case 4, 5 has been known like last year, I think. 6, 7 are not interested because they have an even number of edges. 8 was done 2, 3 months ago by Yi. And just after that, even that we don't know. So there is a given current conjecture saying that the Odd-Ramsey number of any click should be subpolynomial, but it's wide open. And it's quite interesting, mostly because I could talk about the fact that the t equal 4 is kind of a limit case for some problem. And so that gives you usually upper bound. There is one lower bound, which is quite nice. Verstegen last year proved that for any graph H, the Odd-Ramsey number is at least logarithmic. So not even polylog, logarithmic in n. And he showed that for most graphs, almost all of them, in the sense that if I take a random graph, so with probability tending to 1, it's going to be polynomial in n. So we know that for almost all of them, the Odd-Ramsey number is at least polynomial, and we believe that the clicks are kind of the exceptions. So it's quite nice. There's a lot of very nice open problem in the domain. And so what we did with my co-authors is when we were reading at everything, and after complete graph stars and matching, we actually went back to the original problem. If you look at Gil, Kalai, Post, and what they were discussing, they were actually discussing what's happening with complete bipartite. So we studied 3 different ranges. The first one is when in the complete graph on 2n vertices, you want to look at what's happening for k and n. So it's a bit specific. It's not like quite often in Ramsey theory, you have one big graph, Kn, and n is going to be very large, tends to infinity. And you try to say what's happening for like maybe a triangle, something that is fixed. Well, here we look at, like we've got what you call Kn, and so it's going to be like what we call a spanning subgraph. So that graph grows with the host graph. And more generally, we're going to be looking at what's happening when we've got just kt and minus t. So it could be unbalanced complete bipartite, but it's going to be spanning. We're going to be looking also at what's happening if you try to color such that every one of them, like not for fixed t, but all of them. You want that every possible complete bipartite graph contains a node color class. And of course, you will be also looking at the case for complete bipartite graph. So this is everything we did, and I'm going to show you after that the precise result. But yeah. And what's, I think, a bit, maybe not funny, but at least interesting, is that we've got 3 cases, 3 very different cases, and we have 3 very different proofs. So today I will be talking mostly about 1 and 2. 2 is, I think, the one I love the most. But the first one, you'll see, no, sorry, the first one is the most interesting. That one we are using a coding theory result, which was a bit surprising. That one we use the polynomial method. So if you've been doing a bit of graph theory, it's our combinatorics. It's a nice methodology to know. And that one is a more standard application of something close to Kováry-Sosturán, if you've been doing a bit of combinatorics. So my goal today is to present you some proof of these simplified proofs, but it is the kind of problem that is once you know the proof, it's kind of easy, but the tough part is actually finding the correct proof. So I will start with the first case. Any question before I dive into? So I'm going to try to keep up here the definition. If ever someone is falling asleep, you can wake up and go back to it.
En minus t or 2n minus t?
Sorry? In that one, we are looking in Kn. Sorry.
In Kn.
Yeah, sorry. And yeah, that would be in Kn. Sorry. So the first case we are studying is we are looking at what was actually number 2 before, we're looking at the family of all complete bipartite graphs. Okay? So for instance, here I've got K6. It's a graph I want to color. I want to color the edge of K6 such that every copy has an odd color class, and I'm looking at every copy of all possible complete bipartite graphs. So I want that every copy of that one is odd, every copy of that one is odd, and every copy of that one is odd. Look in there. And for that one, we gave a precise answer, exact answer, just depending on the parity of n, which is n minus 1 or n. So it's basically linear in n. So I'm going to just show you the proof because that one is simple enough. And I think it's nice. It's inspired by something that Noga did in the article also. But there's quite often, there's two aspects of the proof, upper bound, lower bound. That should be simple. The first step is to show that n is actually an upper bound. So what does it mean for that equation? I want to show that the Odd-Ramsey number of my family is at most n. So it means that there is a way for you to take the complete graph on n vertices, to color the edges of that graph, such that every copy I showed you before, contains an odd color class. And it's a tough proof. Here it is. It's very complicated. So quite often showing upper bound for Ramsey number, at least for these ones, it's simple enough in the sense that you just have to show a coloring. Here it is. You have to find it. That one is simple. We've got other cases that are much more complicated. But once you know it, there it is. And I claim that it's coloring such that every copy has an odd color class. So what it is, it's a path on n vertices in here, such that every edge has a different colors. So it's a rainbow path on n vertices. And then you've got one last color that I'm not showing, but it's there. Okay? So we've got n minus 1 edges here, so n minus 1 color, and the additional one is n. And the good thing is, if you gave me any complete bipartite graph, kt n minus t, you kind of partition its vertices in two blobs. So you know that you have at least one edge from that path that's going to be between the two blobs, at least one. And that one is a unique edge color in that color, so it's going to be odd. So it's a very simple proof that the Odd-Ramsey number for that family is at most n, because you can actually find the coloring. Now I want to do the other direction. I want to show that when n is even for parity problems, but we can assume that, that the Odd-Ramsey number is at least n minus 1. Okay. And what does it mean? It means that if I gave you kn, you color the edges of kn with n minus 2 color, so one less, that I know that it's not odd for every copy. So I know that somewhere in my coloring, there is a copy of kt n minus t for some t, you don't know which one, such that every color class is even. So you have a coloring of the complete graph of n vertices with n minus 2 colors. I know there is a complete bipartite graph in there where every color appears an even number of times. So how do I prove that? So, okay, first thing you do, you fix a coloring. N minus 2 colors, you fix the coloring of kn with even. And I'm doing something a bit unexpected, is that for every vertex, so 1 to n, I'm going to assign one value, xi, from the finite field of two elements, so 0 or 1. There's Z2 or F2 if you want. And the good thing is when you do that, it induces a partition of the vertices in two blobs. Okay? So you can put in the first blob all the vertices that get 0, the second one, all the vertices that get 1. Okay? And remember, somewhere here, I've got all the edges, and I've got a coloring. I fix my coloring. So I'm going to build from this one, from this value of xi, I'm going to build a system of equation. Okay? And I hope it's understandable. But so the first thing I do is for every color, so for instance, let's look at my first color. Let's say that that's blue, that's G1 in my coloring. I've got my blue graph here, and I've got a partition induced by my assignment xi. Okay? And what I asked, my equation is asking that if you sum over all the blue edges, and you sum what you sum the value at both ends. Okay? You look at every edge, and you sum the value of both ends of the edge, and you want that the total sum is 0. So that's my equation. That's what I'm going to ask for. And what does it mean for that equation? it means that if the sum is 0, first I can ignore the edges that are inside the blob, because look at that edge, both ends are 0 or both ends are 1, the sum is 0 modulo 2, so you don't really care about this edge. So if that equation is satisfied, it means that you look at the edges that go across here. The total sum is 0. So the total sum is even. But every edge contributes 1 exactly, being 0 and 1. So I know that I'm going to have an even number of edges between A and B in that specific colors. So somehow, if I can find an assignment of xi into 2 blobs such that this equation is satisfied for every color, I know that I have a complete graph, t n minus t, such that every color contains an even number of cases. So how can I ensure that I have an assignment of my xi over Z2 or F2 such that I have that system of equations satisfied? It's a theorem. It's called the Chevalier or Chevalier-Warning theorem, depending on the version you might use. It's a polynomial equation methodology, very strong. It says that if you have a system of polynomial equation on n variable, so it's good for me, I've got my xi, I have n vertices, I have n variable, over a finite field of order q, fq, and such that the sum of the degree is less than n. Here, if you sum, it's n minus 2, I'm good. And if you know that the trivial solution 0, 0, 0 is a solution, then it's claiming that you have another one. And for me, it's good because clearly, if A, my blob A, if I put 0 to everything, here, I know that clearly the sum is 0. So I know that 0, 0 is one solution. It's telling me that it has another one. Except there's an issue here still. What could happen is I put 1 to everything. If you put 1 to everything, to every xi, it's a degenerate case where you've got everything in the same blob B here. So you don't have a complete bipartite graph. So what we do, we just add one equation. There's dozens of possibilities. That one is just to ensure that you have at least one value, which is going to be 0. Okay. We could have asked to say just x1 is 0, for instance, maybe simpler. But we are just adding one simple equation to ensure that you have at least one here that is 0. So we know that the solution 0, 0, 0, it's a solution to my system of equation. I know that all 1 is not a solution to my system of equation. And by the theorem, I know that somewhere there is a solution. So if you have a solution, it means that you have a partition of the vertices in 2 blobs such that in every color, the number of edges across is even. So you know that the Odd-Ramsey number has to be bigger than that. So here, 1/3 of the article done. So that one is the first one we solved. It's quite nice. It's not always easy. We try to generalize to other cases. It's really not easy. It works well here because it gives you a partition in 2. So you can have a nice case. But as soon as you need more than 2 partitions, it's a bit more complex. But the Chevalier warning is a very strong theorem that you should know, and you might be able to use it sometimes. It's stronger than that. It even tells you that the number of solutions has to divide the order of the finite field. So it's quite nice. So an equation for that case. So the first one, I'm going to switch. Okay. What time is it? Oof, I'm going to speed up a bit. And the second one I want to talk about is the one we spent so much time on that case. And it was the initial problem we were looking at. And we are looking at what's happening when you have one spanning graph. So I told you what was a spanning graph before. You have Kn, and you want to have one Kt n minus t. Okay? So now you fix t. Before I was looking at the family of all possible complete bipartite graph. Here I fix one t. Okay? And I'm interested in understanding the Odd-Ramsey number for that value. And the theorem you managed to prove is in different steps. There is a specific case for the kind of middle ground where n is even and t is also even. Then the Odd-Ramsey number of ktt is t plus 1. Otherwise, if t is odd and n is odd, then you have t plus 2. And if t is even, we don't know exactly. We've got logarithm, log n bound here and here. So we know that asymptotically, at least, we've got log n. So here I'm claiming that I cover all the cases because all the other cases have an even number of edges. So this all we care about are here. We have precise value for here and asymptotically tight values at least for here. And you're lucky I will not go one by one and look at everything because we managed to prove a theorem that gives you everything at once, at least kind of. And that was a surprise because initially when we started looking, we have actually like alternative proof of all of these facts, of most of these facts, until we found a way to solve everything. So how do we solve everything at once? Is we need to take a small detour. And to do that, we're going back to coding theory, which is quite nice because the problem started kind of a graph coding theory problem, but we are going back to it. And I'm going to forget about Odd-Ramsey number for a while now. I'm going to talk about coding theory. So we just need one notion in coding theory, which is what is a k-dimensional linear binary code of length n. And it's just a k-dimensional subspace of F2n. Okay? So you're looking at all binary strings of length n. You take a subspace of dimension k, and it's a linear binary code. Yeah, it's fairly standard domain. Okay, so let's go. I fix t, I fix n. For simplicity, I take t to be less than n minus 2. Otherwise, you just take the opposite, but it's just for simplicity. And I define k, I fix it to be my Odd-Ramsey number. Okay? So what does it mean that k is my Odd-Ramsey number? Is that it means that there exists a coloring with k colors of the edges of kn, such that every copy of kt and minus t contains a node color class. Okay? That coloring exists somewhere, I fix it. Okay. For instance, here, I'm claiming that is the coloring of K6, where every copy of K24 is odd, contains a node color class. And it's a coloring with 5 colors. You don't need to check if you want to check, please. But it's true. Here it is, I fix it. What do I do with that one? Is I start looking at every color. And yeah, let's look at that. So let's look at the first color, for instance. That's my totally colored graph. I look at the first color. And I look at the vertices that have a node degree in that colors. Okay? So for instance, here, we've got vertices 1, 3, 6, and 4. They have a node degree. So I create a set, which is 1, 3, 4, 6. It's a bit weird. And quite often, because it's easier for us to work with binary strings, I create the binary strings, the characteristic vector of my set, which is 1 if my vertex is odd, 0 if it's even. So what I'm telling you so far only is that if you give me a coloring, it gives me like one vector in F2n. Okay? So you do that for the first color, you do that for the second color, the third, and every color possible. Okay? So what you have, it's very simple. There's nothing new right now. It's saying that if you give me a coloring, it gives of k colors, it gives me k vectors over the binary strings. Okay? Fairly simple. And quite often, if I give you that, I'm teaching 136 these days. What you do is take the spanning set. The spanning set of these vectors, it's what we call a binary linear code. So in 136, it will be just a subspace, but because the space is f to the n, it's a binary linear code. So you've got these vectors. They don't have to be linearly independent. So you have a linear code of dimension at most k. We don't know if it's exactly k, but you've got something here. And I'm going to look at the dual of that code. There's a lot of information. But the dual of the code, or the PEP, the orthogonal, if you want, it's just the family of all linear code that have inner product 0 with all of this and everything in here, for the matter. But yeah, you just care about the spanning set. Yeah. So what I get in the end is another code, binary linear code of length n with dimension at least n minus k. So right now, there's nothing linked to odd. Just saying, if you give me a coloring, I can give you such a linear code. Yeah, that's fine. And finally, we're getting there. Assume that you have another vector in here, in F2n, that has weight. So the weight of the vector is just a number of 1. And the weight I'm claiming is exactly t or exactly n minus t, sorry, one of the two. So you've got here, for example, a is going to be 1, 1, and 0, 0, 0, 0. So once again, if I give you such a vector, it induces a partition. Yeah? Here I've got the 1, here I've got the 0. It induces a partition, and you look now at the graph, the complete graph between the two. Yeah. So what do we have? Is by definition of my coloring, now we're going back to the definition. My coloring by definition was such that every copy of kt and minus t had an odd color class. That was the definition. And my vector here, because it has weight t, it induces a partition in the two, so it induces a copy of kt and minus t. So I know that in that coloring here, there is an odd color somewhere. So let's say that it's the first one, I don't know, teal, I guess, that's teal. Yeah. So we have an odd number of edges. So we know that here we have an odd number of edges, but if I want to count in theory, in my coloring, how many edges I have from A to B in that color, you can just do a degree counting argument. Degree counting argument, it tells you that you just count over A, all the vertices of A, you count the degree, and that should give you everything you have in between, plus twice the number of edges in A. Okay? And now I'm going to work modulo 2. So what's happening modulo 2 is that coefficient that is twice the number of edges you don't care about. So now you're just counting here the degree in A that are odd, actually. So because if here I've got a degree that is even, it's going to contribute 0, while if it's odd, it contributes once. Yeah. So now I'm counting the number of vertices that are odd in my graph, in A. And by definition of that was exactly the definition of my set S1. And so by definition, it's just the inner product of A with S1. For instance, if S1 was my graph 1, yeah. Okay, so the number of edges between A and B, modulo 2, is just the inner product of A times S1. And because I know that my color class is odd, so I know that the number of edges between A and B is odd, I know that the inner product is 1. So what do I know? A is not in the dual. The definition of the dual of a linear code is that A should be 0 with the inner product of every one of the spanning one. So what I did just prove to you is if you get me any code of weight t, it's not in a dual. So it's everything. It's a bit long, but I'm claiming that we are done now because we show that if you gave me k, which is the Odd-Ramsey number here, then there exists a linear code of length n, dimension at least n minus k, which is the dual was dimension at least n minus k, that avoid code words of weight t and minus t. And you can believe me, you can add here n without losing anything. It's a small trick you need to do in order to reverse everything. And I don't want to spend too much time in there. But I just showed you that if you've got the Odd-Ramsey number, then you've got a specific code with dimension quite large and avoiding some specific weight. And the good thing here is if you've done anything in coding theory, people love that kind of problem. And we know a lot about things in that kind of problem. So it's a kind of a generalization of just asking for the minimum distance of a code, for instance. But here you're avoiding some specific weight. So what we do is you define, if you want, the largest dimension possible of a binary linear code of weight, avoiding weight t and minus t and n. And what we proved is that parameters is at least n minus our parameter. And again, you're going to have to trust me. It's not too complicated. But everything I showed you, there is a way to reverse everything. So if you give me a code, I can build a coloring and so forth. So what we managed to prove is that these two parameters are actually like equal or symmetric compared to n. And that's when we solved everything more or less. Because once you have that kind of result, you can use, there is a lot of things that exist in the bibliography, in the literature. Some of these results come from like the 70s, some are a bit more recent. Some of the results I've shown you before, we're just applying the Hamming bound, if you know what that is. But just using these results, we got everything. So everything I showed you before is because you apply a specific result. That one is from Enomoto, Frankel and Ito. That one is from Nomura. No, the number is here. Mazurov. That one is just a Hamming bound. That one is coming from Cohen and all. So it's just when we found that result, it was nice, but everything we had before was like, okay, it's solved now for everything. So we were like really happy. We don't know exactly if there is something bigger under that, because it feels that the initial problem was in coding theory, more or less, with graph codes, and we solved it using coding theory. So we are wondering if there is something lurking beyond that is deeper, but it's, the link is quite complicated, so maybe not. So that's how we solved everything in there, almost, at least asymptotically. And the last domain, do you have any question about that before I go? I will not talk about the last one, so I've got time. And the last domain, maybe now the most interesting remaining one, is understanding what's happening where you just want to have every copy of a fixed KST. So not spanning anymore. Now KST is fixed, Kn tends to infinity. And we just have bounds. We didn't spend too much time on that because it was already too long. But the upper bound comes directly from the generalized Ramsey number, raised by Aksenovich, Furedi, and Mubai on this number for complete bipartite graph. And the lower bound is, it's a bit interesting, but it's a bit long for here. It's, we just took the Kováry-Sors-Turan. Kováry-Sors-Turan, if you don't know, it tells you that if you have a graph with like high density enough, you must have in there a complete bipartite graph. So it's kind of a pigeonhole principle you apply. If you don't have enough colors, the Kováry-Sors-Turan will tell you that you have at least one monochromatic KST. So it gives you a bound for the Odd-Ramsey number. And what we did is we took that proof, the proof for that theorem, and we did a lot of changes in there just to adapt to our setting. And it gives you, we managed to improve by the squared. So we took a square of that more or less. But there is still a lot of discrepancies between the two. So we'd like to understand better what's happening. But that's for the rest. And yeah, there is a lot of open problem. I told you we solved almost everything, except here we only have asymptotic results. We'd like to understand what's happening exactly, but we have not much hope because it's open in coding theory. And people would love to solve that kind of problem in coding theory. So I believe that we cannot do better. That one, we believe we can do better. Probably that bound is not true, and that bound is not true also. So because it's a bit weird, but more or less here, it's like asking for a monochromatic copy, while here we've got edges with a unique colors, like one. So we know that probably both bounds are not correct. And just to finish, there was something that was published just like 2 days before we published our, so that was a bit annoying. But they published a variant on that, exactly on what I was saying. Instead of asking for a single copy on odd number of edges, you want a unique color, like a color that appears once. And we did some additional work. We say, okay, we've got like a few days to do. So we just managed to find some values for that parameters to compare to what we had for the Odd-Ramsey number. So everything I told you about Odd-Ramsey number, we cannot manage to move easily into the setting of unique Ramsey number. But every time we do that, we've got something that is proportional between the two. So we'd like to know if there is a family such that the two parameters are actually a polynomial away from each other. But that is too much here, but that's something I'm really interested in. And finally, the one I was obsessed with for a year, and I didn't manage to solve yet, is if you go back to the initial problem of graph codes, if you're interested in that, understanding what's happening already for C4. So to have a code such that the symmetric difference between any two graph is isomorphic to C4, and to have that code as large as possible. We have bounds. I've got 3 proof for that one. I've got 3 proof for that one. And I cannot improve any of them. So it's really annoying. But that's how I got into the problem initially. But yeah, it's a newish study. There's quite a lot of people working on this kind of problem now. It's quite interesting. There's a lot of open problems. So hopefully we get some new stuff soon. And yeah, it's been fun. So thank you.
Thanks. If there's any questions. wait for the mic.
Does the notion of an even Ramsey number make any sense?
So you want that every copy of a graph has a, well, edge is going to be odd now. Well, no, an even number of edges. Yeah, probably. You need to understand, to explain why you care about that one, but maybe you don't. Like that one came here because of that formula, clearly. But an even number of edges, you want every copy of H. An even H has to be odd itself or even itself. Yeah, you could look at. I don't know if it's trivial or something. Sometimes in these kind of problems, it end up to be trivial, but yeah, maybe.
I have a question. So you mentioned that you had 3 separate proofs.
Yeah.
And then you kind of unified them all with this coding theory approach.
Well,
are those proofs worth?
No,
do you want to tell us a bit
the
about
coding theory ended up just doing that. Oh, yeah, initially, yeah. Sorry. Yeah, go on.
What were these other? What was the other proof technique?
It was very different. So for the upper bound, it was just finding a correct coloring. So the same way when I did the proof, the initial one is just here the coloring. It's nice. For the other case, it was just finding the coloring. I don't even remember how we found the lower bound. It's a bit sad, but what we did without realizing it is we did everything that the coding theory aspect and reproving some of the coding theory bounds in the end. That's how we made the link with coding theory. Is at one point we realized that we were just building a linear code. And you could do that maybe in different place. But it was more or less redrawing everything that is known in coding theory. So yeah.
Any more questions? All right, then let's thank Thomas again.
Thank you.